formally say it. These theorems and converses, they are in your theorem and postulate sheets. Okay, so we're talking about isosceles triangles. Remember the big thing about isosceles triangle. The only thing that's important about isosceles triangle is it has at least two sides that are congruent. Doesn't matter about the angles. You could have a right triangle that's isosceles. You can have an acute triangle that's isosceles. You can have an obtuse triangle that is isosceles. To be isosceles, you just have to have two sides that are, in fact, congruent. Now, the two congruent sides are actually called the legs of it. Those are called the legs of the triangle. Oop, not legs, don't have an I. The legs of the triangle. It actually comes from more trapezoids, but these are called legs. So the legs of an isosceles triangle are the two that are congruent. Then where the legs intersect, that is called your vertex angle. So that's that angle that's included between our two congruent legs there. The side opposite the vertex is called the base. Now notice I said it's opposite the, stop, keep it on. Opposite the vertex, your base does not have to be on the bottom. I can draw an isosceles triangle upside down, your base would be on the top then. So base doesn't mean bottom, it just means across from your vertex angle. Then we have the angles that are connected to the base, those are going to be called base angles. And your base angles are going to be really important because we're going to lead to the first theorem that's specific to isosceles triangles. This is the theorem. The next one will be the converse. We have to keep track of which one's the theorem and which one's the converse because they're really close. Remember alternate interior angles? We had a theorem if I had parallel lines. We had a converse if I need to prove their parallel lines. So likewise, these two things are going to be very, very close. You just got to remember which one's your theorem and which one's your converse. The theorem says if two sides of a triangle are congruent, that means I have an isosceles triangle. So if two sides are congruent, this basically says if I have an isosceles triangle, then the angles opposite those sides are congruent. So if you have an isosceles triangle, base angles are in fact congruent. So how we could use that, so if we looked at the picture over there, so if I have an isosceles triangle, so basically if we can say that AB is congruent to, I guess, BC or CB, doesn't matter, then those angles opposite it will be congruent. So if I have an isosceles triangle, then 2 and 3, or angle A and C, would be congruent. Then A will be congruent to C. So if I have an isosceles triangle, base angles are congruent. If you're given isosceles triangle, then your base angles are congruent. The converse says if two angles of a triangle are congruent, so they're basically saying if you have base angles that are congruent. So if I give you a triangle with two congruent angles, then the sides opposite those angles are congruent. So think about what this says. This says if I have two angles that are congruent, I have an isosceles triangle. I have two sides that are congruent. So in a proof, it might look something like this. If I could show that angle A is congruent to maybe angle C, then you have an isosceles triangle, so that means two sides are congruent. So then I would have AB is congruent to that BC. So the theorem's used if I know it's an isosceles triangle. That means I know two sides are congruent. The converse is used to prove it's an isosceles triangle. So your converse goes from angles to sides. The theorem goes from sides to angles. It is important in a proof for you to say whether using the theorem or the converse. So one more time, the theorem starts with an isosceles triangle, so base angles are congruent. The converse says if I have base angles congruent, then my sides are congruent, so then I have an isosceles triangle. So if I need to prove something's an isosceles triangle, I'm probably using the converse. If I'm using an isosceles triangle, I'm probably using the theorem. All right, let's use some facts with that. Not proofs, just some simple problems here. So it says find the measure of each, and we're supposed to list the theorem that I used to come up with that information. So we have an isosceles triangle. So what does that mean? Yeah.
The measure of angle J, I guess both the bottom angles would be the same.
Both of these angles would be the same. Yeah, perfect. So we could go ahead and say that J is 68 degrees. Would this be the theorem or the converse? This would be the theorem. We could just put theorem down there so we know where we just got those theorems and converse. We're just going to list, is it the theorem or is it the converse? All right, so that means that I have both of these base angles are 68 degrees. Can someone raise your hand and walk me through how I find that missing angle, Will? If I'm finding K, how do I find K?
68 equals 68.
Yep. And then what do we do with that? So we add it up.
And then subtract it from 180.
And I'm going to subtract it from 180. So at some stage, we have to get away from having to write out the formula every single time. What we should be able to get to is the fact that, this whole thing is 180 degrees. So to get the missing angle, I'm just going to go, you know what? Measure of angle K is just going to equal 180 degrees minus the two known ones. Now, why this is nice is because, do I ever say you can't use a calculator in this class? No, we can always have it in class. It's always good to write things out, but we can just plug in my calculator. 180 minus 68 minus 68. What's the measure of angle K? Yeah.
44.
44. Do we agree with 44? Does anyone disagree? Actually, who agrees? I need some. Oh, yeah. Okay. We look pretty solid there. All right. Our next one. Uh-oh. This one's a little bit different. I have one angle, but I don't know the other ones. Anyone have ideas how to get the other ones? Yeah, Daniel? So we're going to do 180 minus 106. I came up with 74. Do we agree with that?
No.
I have 74 degrees. I agree with 180 minus 106. Does that mean both of those angles are 74 degrees? We have to divide it by 2. Thank you. I knew you had it. I just wanted to go through that thought process. So we have 74 degrees to split between these two angles. So that must mean that we have to do 74 divided by 2. Does everyone agree with 37 for that?
Yeah.
Am I good with that? So both of them are 37. So that means this one's 37 and this one's 37. So we could just put 37 degrees for both of them. Does anyone need me to walk through that again? It's okay. This is something we want to get right on the test because these are going to show up. Where I just give you like a base angle or I give you those things. Okay. Theorem or converse? I use the theorem because I started with the two things, so this would be theorem. So I use the theorem. Anyone has a guess at what the third one's going to be? Probably converse, because you probably got to have one converse in there, right? All right, so I have, this is 77 degrees. This is 77 degrees. Let's find the missing side first. What would YZ be based upon that fact? It's just killing it today.
12.
Why would it be 12 centimeters?
Because both the sides would be congruent.
Oh, because both of the angles are congruent, both the sides are congruent, which is that converse. So this would be the converse, wherever you want to write that. So this would be the converse, and we'd come up with 12 centimeters because both of those legs would be the same. I have 77. I have 77. That seems like 154. What's my missing angle? 26. Do we agree with 26 degrees?
Yeah.
All right, cool. Hey, guys, if you're not quick at doing stuff in your head, just take out a calculator. There's no reason you shouldn't have a calculator at all times, just in case you have to just quickly do anything. Don't rely on everyone else to do the work for you. If you need to use a calculator, use a calculator. I use calculators all the time. Just because I make those dumb little mental mistakes and I just want to make sure that I get it correct. So I just have it next to me on my desk. You look at my desk, I have a calculator right there. Let's get comfortable using them. The problem is a lot of times you get to like ACT, SATs, and you don't know how to use a calculator because you just don't use it. And part of it's on us, because a lot of times we do tests where you can't use a calculator. But I'm telling you right now, just get in the flow of using a calculator, just to double check your work. Still good to use the mental math, but have a backup system. All right, so that's the big things about our isosceles triangles. The next thing we're going to talk about is equilateral triangles. A triangle, look, what does it mean to be equilateral? I don't even have it on here. What does that mean to be equilateral? All the sides are congruent. So if I did this, I could put tick marks on all three sides. So if I told you this was equilateral, we put a tick mark on all three of those sides. Well, when I taught you about equilateral, I said, well, we also have a word called equiangular. And I said, if it's equiangular, it's also equilateral. So those words mean basically the same thing. The only difference is equiangular means that all of our angles are congruent. That's important for us. It's important for me to be able to say equilateral is equiangular because how many degrees do I have to spread between all three of these?
180.
I have 180. And if all three of them have to be the same measure, let's think about that. If all of them have to be the same measure and when I add them up, they equal 180, what does the measure of each angle have to be? It has to be 60 degrees. So as soon as I say the word equilateral, we should already be able to think, oh, all the sides are congruent. To pile on that, if I say the word equilateral, you should think 60 degrees. Because these will be the problems where I don't put any degree marks on there, and I'll just say it's equilateral, and you'd be like, Bishop Pabian, I don't know what degrees these are. I said equilateral. Equilateral means 60 degrees. So I'm going to go ahead and point to equilateral triangle. The new important thing is all angles are 60 degrees. Nice and big. That's really the most important part of this. We're going to go over some other stuff, but it won't be hard. This is the most important part. All this is saying is, you know what? If I ever come across a problem that Ms. Pabian says angle A is equal to angle B is equal to angle C, that means it's equiangular, which means it's equilateral. So if I tell you all the angles are the same, that means all the sides must be the same. So you could go ahead and say, oh, that must mean that AC is congruent to, let's go around, CB is congruent to BA. That's all it says. If I tell you all the angles are congruent, you can say all the sides are congruent. Likewise, if I say all of the sides are congruent, or why didn't I need the lines here? Can someone explain why I put lines on these, but I didn't put segments on here? What's the difference between what's written here and what's written here? It means almost the same thing. There's just a slight difference. Yeah.
Because you didn't use congruent.
Because I didn't use congruent. This means the distance between A and B is the same as the distance. So these are basically numbers. This could be like 7 is equal to 7 is equal to 7. These aren't numbers. These are saying this segment is the same as this segment is the same as this segment. So remember, when you're using measurements, equal signs. When you're saying the segment, you say congruence. So if I say angle B, if I say all the sides are congruent, we could go, or equal, I could say all of the sides are congruent or equal signs. I'm going to go ahead and use congruent symbols, which means I will not use the measure symbol. Means the same thing, but it's subtly different if you're doing proofs. Like I said, not the big thing. The big thing is 60 degrees. If I say you have an equilateral triangle, you think 60 degrees. We should already have all sides are congruent. Now we just tack on that 60 degrees. All right, let's look at some problems. Find each missing measure or its variable. Okay, I have 60 and 60. What does C have to be? It has to be 60. So if you know two of them are 60, the last one has to be 60. It could be because you did 180 minus 60 minus 60. Or you might just realize, hey, if I have two 60s, that means the other one is 60 degrees as well. What does that mean for all of the sides? If it's what? It's equilateral, so they're all going to be the same. Yes, Owen. All of them are going to be the same. That means the only missing angle is 60 degrees, and the missing sides are all 9 feet.
Should we put P like FT at the end?
You can. So Owen asked if he should put FT on there. I'm not a big stickler for that stuff, but if you want to, you absolutely can. All right, number 5 is the one that trips up people a lot of times on the test. Just because all the information they gave you was 3 tick marks. We should be able to get the sides pretty easy, but they asked for all of the angles. Now, if you don't remember the rule that equilateral triangles are all 60 degrees, that's where people get stuck. They're like, there's no degree measure, Mr. Pabian, what am I supposed to do? Can't help you there. You have to know that equilateral triangles, all angles are 60 degrees. So we could just proceed to go, oh, you know what? All of these are just 60 degrees. This should be an easy question if it pops up. But it's just based on you knowing what an equilateral triangle is and that it's 60 degrees. Okay, number 6. It says a triangle PQR is an equilateral triangle. Solve for X and Y. Can someone give me an equation? There's actually several equations that would work on here. Can someone give me an equation? You don't have to solve it. Just give me the equation to solve for either Y or X. Joseph?
9y plus 1 equals 11y minus 23.
Yeah, we can do 9y. Whoop, that doesn't look like a good 9. We can go 9y plus 1 equals 11y minus 23. Would there be another way to solve for y?
You can do 14y minus 59 equals 11y minus 23.
Absolutely, we could do 14y minus 59 equals 11y minus 23. Was there any other way?
Yeah, 14y.
Yeah, 14y minus 59 equals 9y plus 1. All of these are equal, so as long as Mr. Pabian did the problem right, it shouldn't matter which way we set it up. We're going to come up with the same y value. So if you didn't write this exact same thing, if you wrote a different one, don't erase it. See if you can solve it and get the exact same thing I'm going to get. In fact, I challenge you, pick a different one that you set up and see if we come up with the same value. So starting off this problem, maybe I'd subtract 9y from both sides. That will give me a 1 equals 2y minus 23. I would add 23 to both sides. Well, that's not a 23. That's a 23-ish. Then we'll have 24 equals 2y, and we should end up with y equals 12. Did anyone do it a different way, or did we all just copy my way? Did it come up with 12?
Yeah.
Cool. Doesn't matter. All right, now here's the problem. 7x minus 3 does not have anything that it relates to. Xavier.
60. 7x minus 3 equals 60.
Oh, it has to be 60. For an equilateral triangle, all of them have to be 60 degrees. So even though there's no number there, we have to realize that all of these are 60 degrees. So we're just going to go 7x minus 3 equals 60. We're going to go ahead and add 3 to both sides. 7x equals 63. And that's going to be x equals 9. Good with that? X equals 9, y equals 12. Are they really hard problems? Probably not. You just have to remember the rules. And the good thing about isosceles, they're on your theorem sheet. So the equilateral one is not. You have to know it's 60 degrees. All right, questions on any of those problems? All right, those are the really big ones we're using today. We have one more theorem we're going to talk about today. This one only applies if you have a right triangle. This only applies if you have a right triangle. So as soon as you don't have a right triangle, forget about this rule. This rule says, hey, if I have a right triangle, so that means you have one right angle. So if the hypotenuse and the leg of one right triangle, once again, important thing is one right triangle is congruent to the hypotenuse and leg of another right triangle, then the two triangles are congruent. So if you have a right triangle, all you need to know is a hypotenuse and one side. So basically you just need two things, a hypotenuse and a side if you have a right triangle. So just a reminder, for right triangles, the angle or the side that's strictly across from our angle is our hypotenuse. So this one right here is our hypotenuse. Your hypotenuse is directly across from your right angle. So if I look at the other one, the hypotenuse is directly across. This is my hypotenuse. So if your hypotenuse, so this would say if, I guess, BC is congruent to our other hypotenuse, which is EF, and we have a leg, so that could either be BAED or it could be ACDF. You just need another side. In this case, it's AB is congruent to, looks like DE. Then our two triangles are congruent. So that means triangle ABC is congruent to, so I picked ABC. I'm going to say ABC is congruent to DF. No. Is that correct? No. I just heard the no immediately when I said F. It should be what? DEF. It should be DEF. All right, questions? Okay, let's do a proof with it. So a good idea that I'm going to use in this rule in this proof is, see a little right angle there? I probably can use the HL theorem, which means I need to find a hypotenuse. And is it guaranteed that I'm going to use that? No, I might still use side, angle, side. I might use side, side, side. It just depends on what other information they give me. So it says that triangle LMP and triangle MNP are right triangles. If I do not in the picture give you this, you can ask me which angle should be right. If it looks like it's right, it's right. Okay, so we have the right angle, and we also have that ML is congruent to, looks like, what, MN. All right, I'll make sure I didn't miss anything. All right, cool. So let's go ahead and let's mark down what was given. Our first given was triangle LMP and triangle MNP are right triangles. Do not automatically assume you're using height, length. This could be just telling you an angle, so we can use side, angle, side. Okay, so that's my first given. My second given is that ML is congruent to MN. ML is congruent to MN. That is also given, but we should mark our drawing to help us move forward. So ML is congruent to MN. Now, here's a pretty good sign that I'm probably using that hypotenuse leg, because the side opposite the right angles are hypotenuse. So they just named our hypotenuse congruent to the other hypotenuse. Yeah?
You just say like the hypotenuse of the right angle is down, and that's like congruent to MN.
We could say, well, it already says they're congruent.
That's the given.
That's the given. So our job is to find another side that's congruent, because we need the hypotenuse and we need a leg. So that could be proving LP is congruent to PN. So look back at the given. Does it say anything about P being a midpoint or anything? No. Okay. Well, maybe we could show MP is congruent to MP. Is there any way to show that those two things are congruent?
Reflexive.
The reflexive property. We should look for things that are shared. I would immediately go, oh, they have to be congruent between two of them because of the reflexive property. That should be a given at this stage, saying that MP is congruent to MP because of the reflexive property. All right, now real quick, if we're just going through the checklist, this is actually, it kind of looks like side, side, angle, because we have two sides and a non-included angle. We don't have a side-side angle. So before today, that's one of the things you can't use. There are two theorems you cannot use. And that is side, side, side. I'm sorry, not side, side, side. Angle, 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 and side, side, angle. Those are the only two that don't exist. Everything else works. So once again, angle, 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 and side, side, angle do not work. Side, side, angle, what was that?
What about angle, side, side?
Angle, side, side is the same thing as side, side, angle. I was about to say, if you can change around side, side, angle, and it spells a bad word, you can't use it. But everything else you can use. So one more time, angle, 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 side, side, angle, or angle, side, side. Those two do not work. However, we switched this over to be that HL theorem because it's a right triangle, so it opens a door to a new one. And that would be our HL. So we can go ahead and say those two triangles are congruent. And that's because of this theorem we just learned. Do we know a hypotenuse? Yeah, it's across from the right angle, so we're good there. Do we know another side? Yeah, I have a hypotenuse and another side. That's basically what the leg is, a hypotenuse and another side. So this would be our hypotenuse leg theorem. Let's just call it our hypotenuse leg theorem. Or you could just put HL, just like you could put side, angle, side, 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 side. We could just put HL and I'll know what we're talking about. Questions on what we just covered? Basically, we're just adding to our bank of things that we need to know for this upcoming test.